On tonight's show, we're talking about parallelism versus concurrency, threads, locks, mutices, JavaScript, and more. Jump in the thread pool, the water is fine on this episode of Change Mode. This is Change Mode, episode number 8, recorded October 22nd, 2014. Concurrency Models, chapters 1 and 2. Welcome back to Change Mode. It's been a long time. How long has it been, Colby? Do you remember how long it's been?
Oh,
2 months?
I don't know. A long time.
2 months.
Is this my first change mode from Boston?
Yeah, in fact, in this beautiful picture of you on the website right now, I can see your old
Oh yeah.
apartment with your fireplace and everything. Yeah.
It just got nostalgic.
Yes, 4 countries later, 1 move across the country, and we're back. Real quick, you can find all of our shows at our sweet new URL, changemo.de, change mode, because we're kitschy like that. Or at Don't Panic, coffeeandbeer.tv, that's the one I meant to say. And then on Twitter, at Change Mode Show. Awesome. Colby, I'm going to pretend that we haven't talked in the 2 months that we haven't done the show. So what's new?
2 months. Well, I moved to Boston.
Yeah.
I have a new job now. I work at a place called HubSpot.
What do you do at HubSpot?
So HubSpot is building a CRM. So kind of like what Salesforce does, except ours is going to be free.
Nice. So, I didn't know that. I didn't know it was going to be free.
Well, it's going to be free. It's Dropbox style, like free until you hit a certain hit various usage limits.
Right.
But yeah, so it's pretty exciting.
Cool.
Yeah, I've been enjoying it.
You having fun still writing the JavaScripts?
Yeah, they let me write React, so I'm living that dream.
A condition on your employment?
Pretty much, yeah. They seemed really cool, and then they were like, yeah, a bunch of people are starting to do stuff in React, and I was like, well. Yeah, it's been pretty fun though.
Cool.
Yeah, I've there was something else I was going to say. I can't remember it now though. Oh, it is. So it's they trade-offs. I can write React, but I am writing CoffeeScript.
Oh, right. Your quote about compiled JavaScript languages. When you play the game of compiled JavaScript languages, I don't remember what the end of that quote was, so it's not that exciting.
You win or you die.
That's it. But can you really win?
Probably not.
I thought you just die.
Yeah, I think so. Yeah. No, it's okay. It's like the more CoffeeScript I write, the more my CoffeeScript starts to look like JavaScript. The more I just use all the parens and the curly braces and the commas that I could leave out sometimes. And then I feel a lot better about it when I do that.
Okay. So not a fan of CoffeeScript on the whole.
I mean, it does some nice stuff, your variables are automatically locally scoped. You don't have to use the var keyword, and it has short syntax for functions and also for lexically scoped functions, so you don't have to use function.bind everywhere or any that equals this wackiness.
That's the worst. If you
yes. Yeah. So it's got some nice stuff, but I could do without the significant white space and no braces.
Significant white space. Not even once.
Yeah. No, I just think it's really hard to read, to be honest. It's hard to find your place in
Yes, because white space, you can't see it.
That's
right. It's called white space. So why are you making it significant?
Yeah, so yeah. It's fine. It's like anything else. I don't know.
If you want to enforce style, you can do a linting like style checker thing, which I think we talked about earlier on this show.
Probably.
That's the right way to do that.
Yeah.
All right, enough JavaScript. Let's talk about concurrency. So,
Speaking of JavaScript.
speaking of things JavaScript totally does, we can talk about that. Uh, concurrency. So, a month ago, we decided to read this book, Seven Concurrency Models in 7 Weeks by Paul Butcher. It's part of the Pragmatic Programmer series of books, which is a company run by the people who wrote Pragmatic Programmer. But Colby, did you know that the Pragmatic Programmers publishing company does not publish Pragmatic Programmer because they wrote that book before they started the company, so it's owned by someone else.
Interesting.
So we read chapter 1 and 2. Whoops. I pressed the button. Sorry.
Dan swore.
We read chapter 1 and 2 for tonight's show, and then for the next show, I won't be so optimistic as to call it next week, though it could be. It could very well be next week. We don't know. Much like when you write sequential programming, we don't exactly know, or when you write concurrent programming, we don't know when anything will happen for sure. We just know that eventually it will happen. So we read chapter 1 and 2. Sorry?
I said we promise it'll happen.
Yeah, promises. That's coming in JavaScript, right?
Yeah, well, yeah, there's like I don't know if it's ES6 or if it's I could look now, but it's going to be like a like a language feature at some point.
So we might talk about promises, but chapter 1 and 2 are this week, chapter 3 for next time. Chapter 1 is an introduction, but it's actually a pretty broad discussion of concurrency, parallelism, distributed programming, all the different, and a brief overview of all the different models of parallel programming. And then chapter 2 talks about mutual exclusion and memory models, also known as threads and locks, which are sort of the bread and butter of sequential programming, or as I like to think of it, the assembly of sequential programming.
Nice.
So, chapter 1. It begins as all stories begin. It was a dark and stormy night. No. Colby, what's the difference? Unless you know what the promise thing is yet. Did you find that out?
Wait, what? What do you mean?
Never mind. Colby, what's the difference between concurrency and parallelism? Pop quiz. Okay.
So this is one of those things that every time I read it, I think I understand it. But then every time I try and explain it to another person or myself, I mess it up. So parallelism is doing two things simultaneously, correct? Like,
for a certain a definition of doing.
So I think
you're right.
Parallelism is like if you have two, I don't know, you had two computers doing two separate things at the same time. They were doing those things in parallel.
Yes.
Okay. And concurrency is doing two things at the same time, but that could mean that like...
He put, Colby, for those listening, just put scare quotes around doing two things at the same time.
Yeah. So for example, you could have one... I don't know. If we're talking about me, I could be talking about concurrency and parallelism while also looking at Twitter, and I'm doing two things concurrently. But theoretically, I'm only focusing on one of those things at a time. So I have to like context switch back and forth. So I think that sort of reminded me of like our OS class in college when we did like, I just said it, but when we did like implemented context switching in our toy operating system, where like our OS was, it wasn't parallel because it was running in JavaScript on a single thread, but to achieve concurrency, we would, allocate a certain number of clock ticks to one process. And when it used up all its clock ticks, we would swap it out for a new process. And that is concurrent because two things are, again, scare quotes, happening at the same time. But in reality, like, it's the same thing is doing the things.
So yeah, to the user, it appears like things are happening in parallel, but it's actually only concurrent. So if you use like a Windows 95 computer, before there was hyper-threading, which itself, I believe, is still a form of concurrency, not parallelism, but I do not understand how hyper-threading works at all. You could move windows around while music was playing. How is that possible if there's only one thing doing something?
I mean, I guess it's the case that the CPU can do things so fast that it can, decode the music and calculate what the window is going to look like. Well, would it have a graphics card that is calculating what the Windows stuff, or at least some of the Windows stuff?
But I don't know. I think there is some sort of graphics subsystem, even if it's not dedicated on most CPUs. And
like for example, right now, I know there's a way for me to see this. Let me see. I was looking at it the other day. In iStats Pro,
if you click on CPU, you can see what your GPU is doing.
I thought so. Do I have to click on it?
Yeah. And it brings down the drop down. Yes. Okay. So right now my CPU is hovering around 7%, and my GPU is, it doesn't say what percent, but it looks even higher than 7%.
Right. Skype. It's doing all that Skype stuff.
Yep.
Yeah.
Cool. So I think that covers concurrency and parallelism, but there are a couple of different types of parallelism, which I thought were interesting. I wouldn't have thought of these as types of parallelism. The first one they talk about is bit level parallelism, and then the example they give is why is a 32-bit computer faster than an 8-bit one? Parallelism. If an 8-bit computer wants to add two 32-bit numbers, it has to do it as a sequence of 8-bit operations. By contrast, a 32-bit computer can do it in one step, handling each of the 4 bytes within the 32-bit numbers in parallel. Blah, blah, blah. That's why we keep moving up. The total amount of benefit we'll see from this kind of parallelism has its limits, which is why we're unlikely to see 128-bit computers. And I didn't know why that has its limits. I guess because most numbers are under 64-bit. That probably makes sense.
Yeah.
So the likelihood that you'd need 128-bit width on your memory is not likely.
I feel like that's what every successful web service thought about their primary key IDs too.
Yeah, but now we have 64-bit IDs. You only make that mistake once.
That's true. That's
enough for every number to assign a number to every grain of sand on Earth and still have some left over.
Yeah.
And every known star in the universe and still have some left over. I think until we start assigning IP addresses to like everything in everyone's house. Even then, I think we'd still be all right. Or in this case, like IDs for things and databases.
Yeah. I mean, there are a lot of grains of sand, so I think we'll be okay for a couple of years.
The second type of parallel, these are parallel architectures that they talk about. So the second type of parallel architecture is instruction level parallelism, which you might not have learned about, Colby, because you skipped that stupid class. It wasn't stupid. You skipped the class where he talked about pipelining out of order execution and speculative execution.
So what class was this in?
Computer organization and architecture, or architecture of hardware and software. I don't remember. It was one of those two titles.
Yeah, I definitely didn't take the one that was called something like that.
Yeah. So this stuff is pretty bonkers, and it's one of the reasons when in any type of program, but especially in parallel computing, you can't guarantee the order that something will be run in. So pipelining is, uh, I'm not sure I remember, but pipelining is basically, I remember the example we used in class was if you are doing laundry, but you can't do all of your laundry in one go, either because of the size of the washer or because you want to split it in different colors. A naive implementation would be put it in the washer, wait for it to be finished, put it in the dryer, wait for that to be finished, put the next one in the washer. But when you're putting the first load in the dryer, you can put the next load in the washer. So that's like a type of pipelining where two instructions that are actually sequential, the processor can see that they can be done simultaneously. But then if you have multiple of these, you can do even crazier pipelining stuff. Uh, I don't know what out of order execution is, but speculative execution is when, and this is all at the assembly level. So, like commands move and copy and things like that. Speculative execution is when the processor thinks that the next instruction that will come down will probably be this. So it's just going to do it now. And most of the time it will be right. And then the CPU just gets even faster than like the actual clock speed at that point, which is nuts. Uh, but all of this means that even when you're writing assembly, you can't guarantee two assembly programs executed concurrently, what's the other word? Parallel, in parallel, you cannot guarantee that they will execute in the same order every time. Just pretty nuts. Do you have any thoughts on that stuff, Colby?
I don't know. It's just madness. Straight madness.
Yeah. And then it gets even more maddening, and we definitely did this in OS where uh, your memory management unit is not mapping the memory that it's giving that you see coming from it isn't actually memory on disk or on in the RAM necessarily. It could be on disk and you don't know, and it's paging it out for you. Computers are crazy. It's a miracle they work at all. When I heard about that pipelining and speculative execution, like this isn't a program. This is a circuit that's doing this.
Yeah.
That's nuts.
That is pretty impressive.
Data parallelism, sometimes called single instruction multiple data architectures. Basically, what this is you have an operation that's taking place on a set of data, and you have a large amount of these discrete bits, and you say, okay, I can do each of these things in parallel because they don't affect one another. And a good example of this is image manipulation. So if you wanted to like increase the tint of every pixel in an image by 10%, you could just do every pixel in parallel and then assemble it at the end. And that's data parallelism. That's also kind of MapReduce.
Yeah, that does sound like MapReduce.
And then the last one, task level parallelism. And this is what most people think of as parallelism. Multiple processors. All of our computers have multiple processors now. Our cell phones. My iPad has 3 processors, which is pretty nuts. Or 3.
3?
3. Yeah, it's a 3-core iPad with 2 gigabytes of RAM, which
Whoa.
is the holy grail, I think. I've been waiting for 2 gigabytes.
Yeah, that's been a long time coming, I feel like.
Yeah.
This is like, what, the 6th iPad or the 7th iPad?
I have no idea.
Many iPads speak.
Yeah. So, and there are 2 ways that multi-processor computers work. There's shared memory, which is what I think most of us have right now, where each processor can access any memory location because you have one pool of RAM and you have like four processors, but they're all sharing the same pool. Distributed memory is where each processor has its own memory. And this is, I think, typically like a distributed network Hadoop style thing. I don't think there are many like discrete computers that have a distributed memory architecture. Cool.
Sweet.
So speaking of distributed, why is distributed computing a desirable trait for parallel programming?
Uh, so, I mean, because so the number of like CPUs the number of like cores you can cram into a CPU and like CPUs you can cram into one machine is limited.
Yep.
I mean, it is probably increasing, or I mean, it's definitely increasing, right? But it is physically constrained in
Because
like
physics,
heat.
I think.
Yeah, because yes, I don't mean physically like the like space. I mean
Right.
physically like heat and
Yeah.
and smallness. Um, but the number of computers you can acquire is much less limited. In fact, computers are really cheap.
Yeah.
Especially like commodity hardware. So like it's really expensive to get a million core CPU from like IBM. Um, I don't think there's a million core CPU. Just
If
just to
there
be
was,
clear.
IBM might make it.
Yes, I would expect so. But it is way cheaper to get like 8 Raspberry Pis and hook them all up to do one job.
There is a 72 core processor that you can buy.
Whoa.
Uh, but yeah, so scaling like processing, doing work more easily, like scaling that out more easily is one benefit of distributed computing. My favorite benefit comes from the Erlang world when we'll get to Erlang if we finish this book at some point in it. But one of Erlang's big things is let it crash. So in a distributed computing model, because the network is unreliable and you can't guarantee that a unit of work you send to a distributed node will ever return that work. So you have to design your program to be tolerant of these failures, which sounds like it sucks, right? Like, why do I have to worry about if my code's going to execute or not? I wish I could just assume that it would always execute. And that would be great. But I think the fact of the matter is, even in sequential programming, you can't guarantee that your code will always execute. What if it crashes? What if there's a seg fault? What if the power turns off? In a distributed world, any one of your nodes can have any of those things happen to it, and the rest of your program will keep chugging along just fine. And for the majority of your users, everything looks great. So distributed software has a benefit besides just raw processing power in resiliency. Also, like distributing your computers across the world, putting computers closer to the people who are using the programs on them also has benefits and super exciting challenges with the speed of light, which are always fun. We can talk about those some other podcast.
Sweet.
So, on this page, on page 7, Colby, it lists all of the programming models that it will talk about in this book. And I'm curious which of these you've heard of and which of them you've used to write programs before.
Page 7.
Page
Sorry,
7.
I'm like in the Kindle app.
Ah.
So that probably means nothing to me. The 7. So are we talking about the 7 models?
Yeah.
Um, so threads and locks, I don't think I've ever like explicitly used threads and locks.
That's all right. I haven't either.
I,
I've
I
written code around them
yeah,
or in them, but I've never like sat down and threaded things and locked things myself.
yeah, me either. Which I think I'm okay with.
Yeah, we can talk about that in a bit.
Yeah. Functional programming. This is sort of a vague one. Um,
I think it's safe to say you've done
but
that though.
yeah, I mean, I've certainly written functional programs. Um,
And anything besides, because I know you like writing JavaScript functionally.
yeah, but there was a point at which I did some Haskell,
All right.
and I've also been messing around with ClojureScript, which is Clojure in JavaScript.
Yep. And we'll get to closure next week. Next
Yes,
week.
next time. Yes. So speaking of ClojureScript, that's the next one. I'm interested to see what that means. The actor model, I haven't really used the actor model though I've heard a lot about it.
I have, and I love it so much.
Yes, that's what I've heard from you.
And think carefully as you answer the next one.
Communicating sequential processes. Um,
It turns out this is what Go uses.
oh yeah,
Go
that's what,
channels and Go routines.
yeah. So that's actually this is what ClojureScript uses now too.
Oh, interesting.
Yeah, the core async in ClojureScript is a CSP thing. Data parallelism. I have written analytics jobs on at Etsy on Etsy's analytics stack.
I think that's the next one.
Data parallelism or
I think I think Lambda architecture is MapReduce.
oh,
Data
you're right.
parallelism
You're
is
right.
like this
Sorry,
GPU.
I got ahead of myself. I've never done GPUs. So
Yeah, me either.
fuck that shit.
Hey, you don't know. It could be
Maybe
fun. A
that's
couple
true.
weeks from now,
A
you'll
couple
be
weeks
writing some GPU code.
would be sad.
I could see you getting pretty into drawing crazy shapes and moving them around.
Maybe. I don't know. I think it might be more math than I
You don't remember how to make the donuts in calculus with the crazy
don't.
3D shapes? You don't?
I barely passed calculus. I did not work hard for that C plus. I did like it though.
Yeah, it was fun.
Yeah. So what about you?
So I've not really done threads and locks. I have done functional programming. I've not done closure. I love actors. I've done CSPs, communicating sequential processes with Go, but not with ClojureScript. Never done GPU programming and have written many a MapReduce job or implementation.
Nice.
All right. Any last thoughts on chapter 1?
No, I thought it was cool. I enjoyed reading it.
Last night.
Actually, to be honest, I read this weeks ago, and I was like just an hour ago. I was looking it over again. So I was prepared. I was prepared for the first time we were going to do this show, and that was like 3 weeks ago.
That's true. That's true. Cool. So let's move into chapter 2 and talk about threads and locks. I really like the analogy they start off with. Threads and locks program is like a Model T. It will get you from point A to point B, but it is primitive, difficult to drive, and both unreliable and dangerous compared to newer technology.
I I like it the it's the simplest thing that could possibly work.
Yeah, and I had a meeting with our CTO today, and he said something he said before, but he said typically what we try to do, like engineers at my company, is first do the simplest possible thing that could work, and then stop. Because most of the time you don't have to go any further. If it's simple, simple is usually a desirable trait. Unfortunately, although I will contend that the actor model is simple and more effective than threads and locks, but we can talk about that when we get there. But a lot of these uh, concurrency models are not simple because concurrency is hard.
Yeah.
So threads. What is a thread? How could we have threads, Colby, before we had multi-core processors or multiple processor computers?
Well, I mean, a thread could be like we were talking about before, like our processes that are running
Yep.
concurrently, but not in parallel.
What is the difference between a thread and a process?
I think a thread is a like linear progression of work happening. I don't know, like maybe it's a unit of work or a unit of execution that is happening in a program. It could be happening like on a different core of the CPU, or it could be happening like on the same core of the CPU. It could have like one, or like one program could have multiple threads running at the same time, or it could have one.
Yeah.
And those threads could be running on the same CPU, the same like physical thread, or the same physical processor, or they could be running across multiple processors, or like multiple cores, or I guess multiple machines, right?
Um, Maybe. Yeah. Not in most operating systems.
Yeah.
But it could be. So the Stack Overflow answer to this is the difference is that threads of the same process run in a shared memory space shared with that process, while separate processes do not share memory at an operating system level. At a physical level, they are sharing memory, or they can be, but at the to the program through the operating system, the program does not share memory with any of the processes, whereas threads share memory with their parent process. Apparently, I think it's nebulous. And then when we get to Erlang, they have a whole other definition of process that is not that. Uh, cool. So yeah, threads are cool. And in Java, it's pretty simple, but not simple. It's simple once you understand the crazy syntax they're using. But you create a thread object. It has a method called run, and it returns nothing, and you just call it, and it does some stuff. And ta-da! Now you have your first thread. That's right, right?
I think so. Yeah. I mean that's
Yeah.
literally what's happening here. So.
uh, but and then did you understand this yield thing? I feel like they just used it in such a simple example that it didn't make any sense.
Uh
This is on page 11.
oh yeah. A hint to the scheduler that a current thread is willing to yield its current use of a processor.
But in their example, the current thread is the parent process, not the thread that you're starting. It's hard to read because there's a page break in the code. The word.
Yeah, that is hard. Um,
But anyways, whatever that is. So you in this example, they have a thread that prints hello from new thread, and then after that, they in the parent process that instantiates that thread, they have a hello from main thread after.
Yeah. So I'm going to take a stab at this yield thing, and I think what it's saying is that if you weren't yielding, that thread that you didn't yield would like hog the CPU. It would basically like use the CPU until it was done.
Mm-hmm.
But by yielding, you that thread will be like, okay, CPU, I'll take a break for a little while and let somebody else go. And if you didn't do that, like if you didn't do that, there would really be no reason to be running using threads at all. You might as well just have them.
Yeah, totally. Good point. So they have these two threads that are printing, and they start them at the same time conceptually, but they could run in any order. So if you were to write this code and run it, you'd end up with a random, also known as equal distribution of the two permutations of the first one and the second one, and the second one and the first one, which just goes to show you that you cannot know for sure when anything will execute. So how you might get around this, locks, also known as mutual exclusion, also known as mutexes or mutices, as I like to call them, but I don't think anyone actually calls them that. Have you heard of a mutex before, Colby?
Yeah, I don't
Have you
get
ever?
it.
You don't get it?
No, well, I guess I get it, but it was one of those scary words that I don't really understand because I write JavaScript.
uh, oh, that's funny. So mutexes are really simple. Uh, so here they have a very simple counter class where it has an increment method and it increments an internal variable to that class, count, and then you can call get count and get the variable. Uh, you can picture the assembly for this, right? Like get value from memory, add one to value, store that new value back into memory. And there's a spot in there where two spots where it can be interrupted. It can get out of memory, and then some other process thread can come along, also get it out of memory, increment it, and write it back before before the operating system scheduler tells our thread to go again. And now all your data is messed up. You've now incremented to the same number twice. Uh, and there's a million, or not a million, but at least three variations on that theme, or at least nine. So in Java, they have this really cool thing, synchronized. So instead of saying public void increment, you say public synchronized void increment. And what that does is it magically handles a mutex for you. So when a thread enters into increment, it sets a mutex, a lock, mutual exclusion, saying, I'm running this function right now, this method. No one else can run it until I reach the end and release the lock. And then the next person can run it. So in this case, you end up with a counter that will always increment atomically. Cool. Not especially useful, but very cool. Something that you'll definitely remember. So the thing they say in this book is, oh, you'd be tempted then to make all of your functions synchronized. But that defeats the whole point of doing concurrent programming, because then everything's pretty much running in parallel, just shifted between them. So what's the problem with locks?
Well, so I mean, I see two problems, right? One is that you have to like synchronize your code, right? So that's like like if you have two threads or more threads running off the same memory, like they will be like their ability to run will be limited by the other threads that are sharing that memory.
What is that called? I just encountered this yesterday.
I don't know. I probably should know this.
Contention.
Yeah, that's the word.
Yeah. So
Um,
yesterday, uh, working with this thing called HHVM, and we noticed that. Uh, oh, I sent you this screenshot. So
mhm,
the performance gain I sent you was caused. The performance degradation was caused by contention. So what was happening was, uh, every time a request came in, this program would look at the file that was being asked for. It had it in memory, but it would check the disk anyways, just to make sure it didn't change. But because that the path to it was relative, it had to call the real path system call, which is super expensive and locking. Because while you're calling real path, you don't want anyone to come along and change the path of the thing you're real pathing, because then the thing you got back wouldn't be the
mhm.
path anymore. So while it's calling real path, this is a multi-threaded thing. Other things, other requests are coming in and also want to check other files, but they can't because real path is locked on that first one. And this is fine with 5, 10, 50, 100 threads. But when you're talking about several hundred threads, real pathing every 20 milliseconds, then contention becomes a huge problem. And
Right.
all the things are slowing down, waiting for everyone else so they can get a lock on real path. So yeah, contention's a huge problem. What's even worse than contention though?
Deadlock.
Yeah. What's that?
So deadlock is when um I think so when one thread has a lock on one piece of memory and is waiting to receive a lock on another piece of memory, and another thread has like a lock on the other piece of memory and is waiting for a lock on the first thread's locked piece of memory. So neither thread will ever continue because both of them, they have like a circular dependency between them, and that dependency will never be resolved.
Yes. Uh, and resolving circular dependencies is that what is that called? It's the something problem. Uh,
Is it like cycle detection or
yeah, but it's like a typical programmer joke. Uh, I don't remember. Anyways, it turns out that that sort of circular dependency deadlock is undetectable. You can never know from within the process if you're in deadlock.
so sad?
uh, which is crazy. Also, if you're the parent, like, well, we can talk about that. But what's the canonical deadlock example?
Is this the chopsticks with the philosophers one?
Yeah,
This
dining
is
philosophers.
so stupid. Who came up with it?
I didn't know you were such a hater on dining philosophers.
I started reading it and I was like, God, I hate this. I remember I don't remember. I remember talking about this in class one time. And
Yeah, one
I think
time.
I
I think
thought
we
it
talked about it for a couple of weeks.
probably. I think I disliked that too. I it's just silly. You can
So,
explain it.
all right. So you got five philosophers around a table and five chopsticks. Chopsticks are pretty useless for eating unless you have two of them. So, uh, any philosopher who wants to eat needs to grab two chopsticks, which leaves at least three other people totally out of luck. So, say it's you, me, and Sean, and two other people, and you and Sean grab two chopsticks. So, me and my friend Bob and Nancy, we only have one chopstick to go between the two of us. So Bob might ask Sean for his chopstick when he's done, and Nancy might ask you for your chopstick when you're done. and then we're all asking for the other one, and there's so many different ways it can play out. But a lot of them end in deadlock, not all of them. Uh, but eventually, if you ran this forever with just people randomly deciding they're hungry and wanting two chopsticks, it will eventually deadlock. And I think in this book it said they typically run very happily for hours on end. My record is over a week, and all of a sudden everything stops uh, because it's deadlocked. There, each person only has one chopstick now, and they don't want to give it up because they need two. But unless someone gives it up, no one will be able to eat, and then they all starve and die, which is a very, very terrible way to go.
Sad times.
So, what do you hate about dining philosophers? I'm just curious.
I don't know. Just like, why are they sitting at a table together? Why are there only five chopsticks? Like, why?
You mustn't have liked your philosophy classes very much then either. These are
Um,
five dining philosophers we're talking about. They're not the most practical people.
that's true. I think I enjoyed philosophy, but that was a long time ago. I took philosophy like before,
Before it was cool.
well, before I would did computers. I
Oh,
that was
whoa.
like freshman year. But yeah, I don't know. I've become too practical.
Maybe that's a not a good thing.
I don't know.
So, how do we avoid deadlock?
Don't use locks.
That would be one way. What's
um,
another way?
I don't remember. Uh, it's
So
something about
what's one a principle you should apply to locks when you are writing locking code?
use them sparingly.
Yeah, don't hold the lock out. Hold the lock over as few lines of code as you can.
Yeah.
Is that decreases, I mean, that's just less time, CPU time that lock will be held, so it's less likely that contention or a deadlock will happen at that point. My favorite one that they say in this book, don't call alien methods, which got really exciting to me because it verifies one of my favorite uh, computing philosophies. When in doubt, pass it in. So an
I
alien
like
method would be like you're in class A and you're going along and you're like, oh, you know what I really want? I really want to pass in the internal state to class B, like a static method real quick and just grab that value out of there. And it's just so easy. Done. One line, boom. You're like, perfect. This sucks for a number of reasons. You can't test that class anymore because you have to mock out the other class B, and if you're in PHP now you can't do that. So now you're like calling runkit to
it.
it's a disaster. Uh, Also, uh, and what is this is typically called? So the solution to this is called dependency injection, which is the D in solid programming, which I think we've talked about before,
Probably.
where you pass in an instance of class B that has this method, and now that instance of class B is part of the internal state of class A. Nothing else will be touching it, and you can mock it out way more easily for tests. But in terms of concurrent programming and parallel programming, if you call an alien method, it's possible that you're calling code that will lock for a really long time. You have no idea what's happening in there. Or it could deadlock because you've caused a deadlock and now your code will never finish. Whereas if you take in an instance of an object, it's just less likely that it's only you who's going to be touching that bit of memory. You don't have to worry about other processes coming along and putting locks on variables or methods that you're trying to call. It's yours. You can do what you want with it at the cost of some RAM, but RAM is cheap almost all the time these days. So yeah, that's don't call alien methods.
Nice.
Really what it means. And I think So if you take this to the logical conclusion, right? You're like, all right, well, don't call it alien method. So my thread is going to be this self-contained thing. We pass it explicitly everything it needs to do its job. You're starting to look a lot like the actor model at this point, where your thread receives messages, it does data stuff to those, it does stuff to that data, and then it sends back a response. And it's like, oh, it turns out that's actually a pretty good model. Anyways, uh,
For another day.
yeah.
Two times from now.
Yeah, to be continued. Uh, Now we get into some stuff that I have certainly never done, except for copy on write. Have you ever used the thread pool before, Colby?
Nope.
No, I didn't think so. I don't really know what a thread pool is either.
Copy on write.
Copy on write.
That's what PHP does, isn't
That's
it?
what PHP does. Yeah. What's
Yeah.
copy on write?
So in well, PHP, for example, when you pass a reference to a function,
I think array is the simplest example.
right. So
you write a function that takes in an array and adds an element onto it and returns it.
So I guess the thing to establish first, so by default in PHP, when you pass an array to a method, that array is passed by value, right?
No.
Okay.
Otherwise, why would copy on write be useful? So
yeah, that's what I mean. Maybe I'm confused.
So here's my understanding. I could be wrong. My understanding is if you wrote a function in PHP that takes in an array and adds an element onto the end, when you take in that array, it is passed by reference. You only get a reference to the original location of that data. Because, well, I'll get to why. And only when you add the other element onto it does it create a copy of it and then add the new element into a new contiguous, not contiguous, a new chunk of memory. And the reason for that is it's way more efficient to pass references than pass values. Because if you're going to pass values, you're copying data. If you pass by value, at some point, like at the assembly level, you can't just lift it out and say, here you go, subroutine, here's some data. You have to like copy it out to a new piece of memory, and then that subroutine talks to that piece of memory. And that copy operation is very expensive. So best to wait to do that copying until you know you need to copy it. If you're just going to read the data, it's fine to read the original representation. That's my understanding of copy on write.
So I guess my point is like if the array is passed by reference by default, why do you need to copy on write? Because you're just writing to the reference, right? Like if you're just changing the reference, maybe an array is a bad example. Like maybe we should be talking about like something else. But like so it makes sense to me if you have a string in a variable, for example. So maybe this is what we should be talking about. We should be talking about like primitives. So you have a string in a variable that is stored in memory location A or whatever. And you pass that string to a function, and that function only reads it. There's no reason that that string needs to be duplicated in memory because the function didn't change it. It can just read from the original one, and everything will be okay.
Yeah, that's what I was saying.
Right, but as soon as it changes it, it needs a new copy of that string because it doesn't have a reference to that string. It needs the value of the string. So like as soon as you change that value, it has to be duplicated and added somewhere else.
Okay. Yeah, that makes sense.
Does that? Yeah. I don't. To be honest, it's been a while since I wrote any PHP, which is
How
weird.
long?
I mean, it's when did probably I moved here on like September 3rd, so it was probably August 27th or August 26th was the last time that I wrote PHP.
So sad.
Yeah, yeah.
Have you writing any Java at least to get your
I
server side kick?
I looked at a little bit of Java. I haven't written any Java.
That's so sad.
I just consume those APIs.
I guess that is the dream.
Yeah,
Yeah, I've been doing C++ the past couple weeks, and it's
that's intense.
the lack of a REPL. The lack of the REPL is what really kills me, especially
Yeah.
because I don't really know C++. It's like, oh, I wonder how like substring works in C++, and it's like, well,
Too bad.
time to write that program
Fire up
all out.
GCC.
Int main, start doing, yeah,
Oh man.
it's not fun. Anyways, you got distracted. So yeah, I think that's copy and write. I don't remember what context they're talking about it in this book. Do you remember? I guess it's just a way to avoid stomping on other people's memory.
Oh yeah. I don't remember either.
Makes a lot of sense. Yeah, that's definitely what it was about.
So what do you know about this re-entrant locks?
Yeah, we talked. So, full disclosure, we're also doing this book club at work, but of course now it's been
Nice.
like a month since we did this chapter. Um, Re-entrant lock. God, what page is that on?
I don't have real pages. Sorry.
Yeah, you do. On the upper right hand corner, it doesn't give you real pages on like the
Upper
maybe
right hand corner.
maybe Kindle doesn't.
I mean, it gives me a location of
Yeah.
which is location
That's no, don't even bother.
717.
Uh,
It's 11% of the way in, Dan. It's
right,
so
28,
it's
30.
interruptible locking. So I assume that means that like if another thread asks for a lock on this, like this thread can yield its lock for temporarily, and control will be returned later.
Yeah,
Hopefully.
and that would be a way to resolve dining philosophers because if another philosopher asked for your chopstick, you could just give it up, and eventually everyone would eat. In the case where if you always yield your chopstick to someone who asks for it.
Right.
Now that you brought this up, I totally forgot when I was writing our notes for what to talk about here. The atomic variables, something I also forget. So atomic variables, right, in Java at least, and a lot of the things we're talking about are Java specific, implements the synchronized increment that we talked about way back in the beginning of this section, where it handles all the locking semantics around like atomic integer has an increment and get method. So that's pretty cool.
Nice.
Any last thoughts on threads and locks? Yeah. How it feels good or feels bad, Colby?
I mean, I think it's pretty scary. I don't know. I mean, I would imagine most of the other things we're going to talk about are implemented using threads and locks.
Just like everything we're doing right now, literally everything is implemented in assembly.
Right. Like at some point that is relevant, but I think as with any good abstraction, this is something that should be like hidden from me as much as possible because it's too hard. I'm not good at programming, so my language should help me out as much as possible.
Yeah. And JavaScript doesn't have any concurrency primitives.
Oh
Correct?
no, it doesn't have any. I mean, I guess
It has the what's that worker web worker nonsense?
so. So JavaScript uses. I mean, I guess in a way it does, um, but they're not. It's not entirely relevant. So the a web worker does not share memory with the current thread.
Mm. So it's a
So
process.
yeah, so you pass it's I mean it's literally message passing. So you pass the web worker some uh I don't know if you can send if you can only full disclosure, I've never actually used web workers before. I don't know if you can only send primitive values or if you can send like complex structures and they're just copied. I feel like you might only be able to send primitive values. So like if you wanted to send an object or something, you would have to like JSON serialize it and send it
Mm-hmm.
over.
Mm-hmm.
Um, but I mean, it works. From what I understand, it works much the same way as like sending an async request. Like you spin up this worker and you pass it something and it has a callback if you want to know, and it passes it back that way. Um, so I don't know, like I'm not sure where that fits into this sort of thing. Um,
Yeah, I think that's a form of concurrency, but not parallelism.
right.
Yeah.
Well,
Well, I guess what I'm thinking of is like the node event loop.
right. So
That's
that's within a single JavaScript process, which you're correct. It is. That's well. I mean, I guess in a way it is parallelism in that like when you kick off an async request, that is happening outside of the node process.
but in a browser context, uh, multiple parts of your JS can be executing at the same time, depending on what events are firing, right?
No,
No. Okay.
JavaScript is like it is strictly single threaded, and it may seem like it doesn't always run in the order you expect you might think it would. Like you can't make it's especially if you're using anything asynchronous. So like anything that leaves the event loop, anything that leaves the JS process, like a network request or like a lot of requests to the browser APIs um, are often not synchronous. So they won't necessarily happen in the order they're written. But they do have like only one thing is running at the same time.
Okay. Cool. Did not
The
know that.
Yeah, so the only exception to that is like the actual rendering. So as the browser is painting the DOM, unless you do certain things, the like actual like recalculation and repaint of the screen is asynchronous.
Mm-hmm.
Um, so and that is mostly transparent. And it's cool because it ends up being really fast. So like your JavaScript can run independently of the painting. So you basically like stuff happens relatively fast until you do something in JS like which forces the browser to like return a value based on that recalculation or painting, which is like a pretty common bottleneck, which will like bring your fancy JS UI to a screeching halt.
That never happens, right?
Like things that should take 100 or 200 milliseconds take like I don't know a second.
Mm.
It's bad news.
All right, so that wraps up our discussion on threads and locks and an intro to concurrency models. As the beginning of the next chapter says, though, about sums up my thoughts. If it hurts, stop doing it. So
Yeah,
we will stop doing threads, and next week we'll talk about closure and how we do functional programming and stuff.
I
Which
have a good closure related story for next week.
cool, awesome. Uh, if you want to get this book, I'll figure out how to use the new Skype and tell you that the URL is bit.ly/change-mode-book. At that link, you can buy the book, and I believe you'll be supporting the show. Or you can at least believe internally that you're supporting the show. I'll believe that you're supporting the show, even if you're not. Cool. So thanks. This has been another episode of Change Mode, and we'll see you whenever the CPU schedule.
This show is brewed fresh weekly by the Coffee and Beer Podcast Network. Get all our shows at our website, coffeeandbeer.tv.